I see Marty's here. So let me just say a few words about Marty and this meeting. Really, this meeting is, in my mind, just the third in a series of meetings. That there was a meeting here in 1998 that led to a paper in Nature magazine, which was the first study that tried to quantify how much carbon emission-free power would be needed this century, and came up with the estimate that we would need to say something like double or triple, produce a carbon emission-free power generation capability that was 2 or 3 times bigger than the total global energy system at that time. And then there was a 2002 meeting that was funded largely by Department of Energy that was a little similar, more similar to this one in focus, which was saying, okay, what are the advanced technologies that could solve this problem, and what are the research goals? But in addition to that, Marty has been he's been my sort of scientific father in that he was both a department chair where I did my PhD, but also Marty's background was in aeronautical engineering, and he's somebody who didn't let lack of formal training prevent him from working on a wide array of areas. And he's made fundamental contributions in ocean modeling, carbon cycle science, and also looking at the big picture at global scale for things like energy systems. And so I think Marty wants to talk about 2 things, I guess. One is I'll let him talk about what he's going to talk about. So with no further ado, we'll hand it over to Marty.
10 minutes is torture for this college professor. I'm going to use my allocated time as follows: 5 minutes for a quick summary of the 98 paper, the 2002 paper, which followed it in Science. And of course, there were 2 AGCI meetings. And I could talk about a lot of the details of those meetings, but I would rather tell you what this has caused me to think about, actually. And it may sound a bit grandiose, but some of you who know the history of science may know in the late 1930s, there was an experiment that was done in Berlin by these guys, Hahn and Strassmann, where they discovered that there was a uranium isotope, U-235, that that was capable of undergoing enormous energy liberating processes so much greater than anything chemical energy could have produced. Only a few people realized this, but it was very important they realized, and not only the physicists in pre-Nazi Germany, but many of the expatriates who were in the United States at the time also realized the significance of that experiment, and through a long series I don't have time to talk about, managed to contact, getting Einstein involved, managed to contact FDR, and created the Manhattan Project as a result of that. And what this makes me think about is that we, although, as I said, I don't want to over-dramatize this discovery, back in '98, when we started to look at the data of what it would take to actively deal with climate change, we got the glimmering that we would need an entire transformation of our fossil energy system, generating 85% of our of the world's energy, and that this would be an enormous technological transformation. Equivalent, we quantified it to 10 terawatts at least of carbon emission-free energy in 50 years. And almost anyone we talked to about it thought that was ridiculous, that climate change would be a problem, but would be one that we could deal with gradually by reducing CO2 emissions. Well, anyway, fast forward to 2016, and we now have a global policy, sort of ratified by the Paris climate talks earlier this year, where almost all the governments, in fact, all the governments of the world, and in this country, with the exception of one political party I won't mention, actually accept the fact that in order to stabilize the climate at 2.5 degrees, something that Ken and I and many of our colleagues also worked on, we basically have to phase out all fossil fuel emissions. And Ken, I'm sure that Ken and Steve and Nate will explain more about why the emphasis on going to zero, why the emphasis on the last 20% of the reduction. So I won't talk much about that, but I would say that this transformation is in many ways is comparable to the way the world was changed when we realized we could have nuclear power and that could be used not only to make bombs, but that could also be used to release energy. It's something that was only understood by a very small group of scientists doing research, basically geeks and nerds like us, who knew that was, implicit in what we were finding. And then I'm sure all of us continue to watch with amazement as every day we see wildfires in dry regions and floods the world over, and we keep saying we can't attribute any one of those things to climate change, but we certainly think that with climate change, with the Earth warming, that's behind it. And so the motivation is very, very strong, and I'm really looking forward to this emphasis on solutions. Scientists and engineers are problem solvers in my mind, and that's actually what we've been thinking about for a long time, even as everyone else is denying that the problem exists. We have a core of people who actually are thinking about solving it, and that's amazing. Now, there are a lot of options on the table, and I don't have time to review all of them. Most of them you know. But I want to put something up that I don't think there's any other presenter that's speaking about, and it's a pretty long-term solution. May I have the first and only slide, please? Okay. Okay. What I'd like to talk about is a development that probably to many people seems very far out, perhaps as far out as controlled thermonuclear fusion, which nobody is speaking about. Controlled thermonuclear fusion, where the world is spending something like $15 to $20 billion to build a fusion reactor in the south of France. But power from space, which actually came up in two of our earlier meetings at AGCI, very few people are pursuing that solution, even though, in my view, there have been at least two technological breakthroughs that make it something that we ought to be thinking about in the near term, not in the very far distant future. How much time do I have? Do I have more than 3 minutes or three? I'm going to assume I have 3 minutes, so I will try to blitz this. The major advantage of power from space is that if you go into geostationary orbit 36,000 kilometers above the equator, which is where communication satellites live and get TV from there, it's a routinely accessed orbit, you have access to sunlight 99% of the time, 7 days a week, 24 hours a day. And given the fact that one of the major issues in getting that to that last 20% or completing this transformation to non-CO2 emitting energy is the problem of storage when you're talking about renewables, both for wind and for solar, which I'm sure this meeting will be dealing with extensively, it's important to realize that there is a source of energy that you don't need, at least the diurnal storage, which is a major problem. There's some seasonal storage issues too. But if you didn't need that, you would basically be cutting a lot into the issue that we need to solve. And you have access to sunlight seven times the intensity in something like 1,400 watts per square meter, compared to an average of 200 watts per square meter at the surface of the Earth over a long time. So that's a great advantage. One of the problems with space-based solar power is all the initial designs were based on transmitting this power from space using microwaves, the microwave part of the spectrum that goes through the atmosphere. But the wavelengths of microwaves are very large, and that makes everything very big. And you have to basically create Battlestar Galactica in space before you get your first power. I'm not kidding. We're talking about transmitters, a kilometer, receivers 10 kilometers in size. You can, however, do the same thing with lasers. That's one of the breakthroughs. We now have diode lasers that are highly efficient. They were only used to be 1% efficient. They're 50% efficient now. That can penetrate the atmosphere. There's an atmospheric window in the infrared where the wavelength is 100,000 times less than the microwave wavelengths of the original solar power satellites proposed by Peter Glaser and John Mankins. And because of that, you can make things much smaller. You can even test it. You could test the idea of beaming power from space to the Earth using the International Space Station. And it's already actually been done for communication purposes. So it's not such a long-term situation. However, you're facing a credibility gap. People can't believe that you could possibly have something cost-effective, a technology that's cost-effective, if the power is coming from space compared to terrestrial solar, let's say. So let's also be fair and say terrestrial solar with storage, which increases the price of PV in levelized cost by a factor of at least 5. So let's say from 10 cents a kilowatt hour, which is what you could do with PV. I have a rooftop PV system that does that, but I use net metering to do the storage. But if you include the storage, the costs go up by about a factor of 5. So you're at 50 cents a kilowatt hour. So anyway, we did an analysis. If anyone's interested in the details, we have a paper that explains all of the numbers and where they come from. But just sort of cast your eye on this. The vertical scale is the levelized cost of electricity over it's a log scale, so it goes from 1 cent per kilowatt hour to $1 per kilowatt hour. And the horizontal scale are the launch costs to place a solar power satellite. This is for laser solar power satellites. To place a laser solar power satellite in geostationary orbit. And that also goes over many orders of magnitude, from $100,000 a kilogram to $100 a kilogram. And basically, I don't have time to go into the details here, but one of the things, the main thing that the figure shows, that if you look at the situation today, we're talking about a nominal cost of 50 cents a kilowatt hour for a levelized cost of electricity, including storage. Now, I'm not saying this is even load following. You guys will be talking about load following systems. This is basically base load system that would be available 24 hours a day from terrestrial PV. At 50 cents a kilowatt hour is nominal, of which about 10 cents a kilowatt hour is the basic PV cost. And at those present prices, if you could put the space-based solar power satellite into orbit, because the total cost of the space-based one is the cost of transporting it into orbit in addition to the cost of the system itself and transmitting it and receiving it, you would break even if you had a launch cost, break even meaning you would get to the 50 cents a kilowatt hour, at a launch cost of something like, it looks like $15,000 per kilowatt hour. That's $15,000 per kilogram, excuse me. Kilowatt hours are for the levelized cost. That's a price. That's a cheap launch. The space shuttle, which is defunct, is much more, and the Russian Proton rockets are a little more. But there are launches you could buy that at, but that's still not cost effective. I mean, none of these systems are cost effective against coal. 2 minutes. Coal is nominally not, yeah? I'm going to stop in about a minute. What I'm saying is that I think we could build a system of power from space that could integrate, laser-based system, that could integrate with ground-based solar through a regional or global grid, which would basically have the capacity for decentralized sources and sinks of terrestrial solar, but would also have the ability to absorb transmissions from orbit to the Earth. And I think we should be evolving towards that system. Buckminster Fuller, back in the 70s, proposed the global electrical transmission net grid before the discovery of high temperature superconductors, by the way, which actually might enable it. And I just want to throw this little bomb out on the table since since I don't see it on the agenda as something to think about. I mean, we need to be thinking about the future. If we're not personally going to be living there, our descendants will, as Jim Hansen says, the storms of our grandchildren are something we really need to think about. Okay, I'm going to wind up if any or two.
Okay, so if there are questions, you're close, so you can.
So Marty, okay, so what do you do once you have the laser, moving, energy back to Earth? What's the energy conversion level?
It's extremely good because what we plan to do is use existing photovoltaic arrays on the ground. If you tune the energy of the laser to slightly above the band gap energy of a photovoltaic cell, that's the characteristic energy level or wavelength at which it absorbs photons, you can get much higher efficiencies than you get for the solar spectrum. So, there's a limit of, maybe 20% or whatever that number is for the solar spectrum, but you're not beaming the solar spectrum. You can beam the actual energy that would be absorbed with a high efficiency. There's no theoretical limit on that other than 100%. Practically, experiments have achieved something like 50 or 60% with lasers beaming photovoltaics. And the neat thing is that you can use the same photovoltaic systems that you're using for terrestrial solar for a space-based system. So you can increase the output of the system. You can beam the power at night and get a total energy far greater than you would with terrestrial photovoltaics. But you've already made the investment in terrestrial photovoltaics. So that's a factor in the economics.
What about the front end, converting the original power you're receiving from the sun to the laser?
Okay, as I said, what you would be doing, first of all, you take the hit on the photovoltaic conversion efficiency in space, just like you take it on the Earth. It's roughly the same, and actually those PV cells were developed originally for space. So you have to take that, whatever it is, 30% or whatever. But then the next conversion efficiency, which is converting the electrical output of the PV cell into the laser, is pretty high. You can buy commercially a 50% efficient laser that will give you coherent photons coming out at 50%. And if you go through the chain of efficiencies, and this is always the argument against space-based solar, that there are so many efficiencies that you lose as you go down the chain. You can compensate for that by the fact that you get 7 times more intensity of sunlight in space than you do at the Earth, and you don't need any sunlight, and the fact that the receiver efficiency, assuming it's a photovoltaic cell tuned to the band gap of the laser, is much higher, maybe 4 times higher than it would be for a conventional PV cell exposed to the solar spectrum. These are assertions right now, not just sort of throwing things out like Donald Trump or something. This is something that there is some background for. If anyone's interested or wants to argue with me about it, I'd be happy to send you some documentation of how I got these numbers.
Marty, we
Yeah.
love to listen to you speak ad infinitum, but
Yeah, it's-
unfortunately, we have a schedule that we need to maintain. So we'll have to
Hey,
thank
it's
you.
great to see you guys.
Thank you
It's
for your
great to see-
participation, and
Thanks, Marty.